Hello guys, welcome on Tesla Adventures. Now we have already studied the numerical problems and the concepts of angular momentum in the previous videos, and in this video we are discussing the numerical problems which are based on collisions and how to use angular momentum in the problems of collision. So in this first question, you can see that there is a rod which is hinged from one of its ends, and the mass of the rod is m and its length is l. Now this rod is in horizontal plane, and there is a ball of mass small m which strikes the rod at this end with a velocity u, and it strikes in such a way such that it sticks to the rod, which means that collision is inelastic. So we have to find out the angular velocity of the rod just after the collision. Now in these kind of questions, we always know that the torque acting about hinge on the system is 0, because we know that on rod there is the only force which will act will be hinge force, and the force of ball will be cancelled out by the reaction force of rod on the ball. So the net torque acting on the system about hinge is 0. So angular momentum, initial and final angular momentum about hinge will be conserved. Now to write down the initial angular momentum Li, we know that this ball is moving with a velocity of u at a distance of L from the hinge. So its angular momentum will be MUL. Okay, and the rod was stationary initially, therefore the angular momentum of the rod initially was 0. Now finally, this rod, let's suppose the rod and the ball are rotating with angular velocity omega, and ball sticks to the rod at the end. So the final angular momentum would be I omega, where I would be the moment of inertia of the system about hinge, and about hinge the moment of inertia of the rod is ml square by 12 plus the moment of inertia, in fact ml square by 3, plus the moment of inertia of this ball about hinge is ml square and into omega. So if we balance out the initial and the final angular momentum, then MUL will be equal to 4 by 3 ml square omega, and cancelling m with m, l with l, omega will be equal to 3u by 4l. So this is the answer which is required in this question, that we have to find out the angular velocity with which the rod will move just after the collision. So it is 3u by 4l. Now let's move on the next question. In this question, again there is a rectangular sheet which is in the horizontal plane, and it is hinged about its center. The mass of this rectangular sheet is m, and there is a ball of mass small m which is moving with velocity u, strikes this sheet at this point and sticks to the sheet at this point. Now we have to find out the combined angular velocity of the system after the collision. So again we can say that the torque acting about hinge, this is hinge, would be 0, and this is for complete system. The system contains this sheet and this ball. So we can say that the initial angular momentum and the final angular momentum of the system about hinge will be equal. This is about hinge. So the initial angular momentum of the system about hinge is m, u and a. This distance is a, so MUA. And the final angular momentum of the system about hinge is I omega, where I is the moment of inertia of sheet as well as this ball. So the moment of inertia of this sheet about this hinge is m by 12 a square plus b square, where b is 2a, so this is 2a square, plus the moment of inertia of this ball about hinge will be calculated by perpendicular, in fact parallel axis theorem. So let us find out this distance. This height is a by 2 and this is a. So this will be root 5a by 2. So the moment of inertia of this ball about hinge will be m into 5a square by 4 and into omega. So L final will be, this is 4a square plus a square, this is 5 by 12 and this is 5 by 4. So 5 by 12 plus 5 by 4 would be 5 by 3 m a square into omega, and this will be equal to the initial angular momentum. So the initial angular momentum was equal to MUA. So cancelling this m with m, a with a, omega will be equal to 3u by 5a. So the correct answer will be option number D. Now we move on the next question. In this question, it is given that there is a rod which is hinged about point A and there is a ball which strikes this rod elastically. Then we have to choose the correct option. So the first option, which says that the linear momentum of the system which contains ball and rod is conserved. So it is incorrect, because linear momentum is only conserved when there is no external forces acting on the system. But in this case, the hinge force is acting on this rod at point A, which is an external force. So linear momentum will not be conserved for the system. So A would not be the correct answer. Now angular momentum of the system about hinge A is conserved. This is absolutely correct, because about hinge A, the torque of hinge force will be 0 as well as the force which ball applies on the rod is cancelled out by the force by which rod will apply on the ball. So for the system containing rod and the ball, the net force is 0 apart from the hinge force, and the torque of hinge force is itself is 0. So the angular momentum about hinge is conserved. So B is correct answer. Now as this collision is elastic, it is given in the question, so kinetic energy will also be conserved. So C is also correct. And the linear momentum of ball is conserved. This is not correct, because if you talk about the ball alone, then there is a force applied by this rod on the ball, due to which the linear momentum of the ball will not be conserved. So the correct answers are only B and C. Now we move on the next question. In this question, there is a particle of mass m which is moving with a velocity v perpendicular to this rod. This rod is of length d and its mass is 6m. It is hinged from its center and this is placed in horizontal plane. So this ball strikes this end of the rod and sticks to the end. So we have to find out the new angular speed of the system. So likewise in the previous question, we know that the torque acting on the system about hinge will be 0 for the system. So the angular momentum of the system will remain conserved about hinge. This is about hinge. Okay, so the initial angular momentum of the system is mv into d by 2, and the final angular momentum of the system will be I omega, where I is the moment of inertia of this system about hinge. So about hinge, the moment of inertia of the rod will be ml square by 12, and the mass of the rod is 6m. Its length is d and md square by 12, plus the moment of inertia of this ball is md square by 4. So this final angular momentum will be equal to md square by 2 plus md square by 4 into omega, and therefore it is 3 by 4 md square omega. And if we balance out the initial and the final angular momentum, then mvd by 2 will be equal to 3 by 4 md square omega, and cancelling this m with m, d with d, omega will be equal to 2v by 3d. So the correct answer will be option number A. Now let's move on the next question. In this question, there is a circular wooden loop of mass m and radius r. So it is a ring, and this is placed on a flat horizontal frictionless surface. Its mass is m, and there is another ball of mass m which is initially moving with the velocity v, strikes this ring at this point and gets embedded or stick to the ring. So we need to find out the final angular velocity with which this system would rotate after the collision. So in these kind of questions in which there is no hinge, we need to find out the combined center of mass after the collision. So after collision, there will be a mass m at this point, and the center of mass of the ring would be m concentrated at this point. So the center of mass of this system, complete system, would be at this point, which is at r by 2 from the both ends, and this is COM, and this center of mass would be moving with velocity, let's suppose it is v dash after the collision, and the system would be rotating with an angular velocity of omega about the center of mass. Now we know that this system is free and there is no hinge anywhere, so we can balance the angular momentum of the system about any point, because torque about any point is 0. So in these kind of questions, we always balance the angular momentum about COM of the combined system. So L initial and L final would be equal about COM of combined system. Okay, so the initial angular momentum about this COM will be mvr by 2, and the final angular momentum about this COM will be I omega only, because this velocity v dash is passing through this point only. So mvr would be 0, because r is the perpendicular distance of momentum or velocity vector from the point where we are calculating the angular momentum. So if we are calculating the angular momentum about this point, then the perpendicular distance would be 0, therefore mvr would be 0. So I omega is the final angular momentum. So I is the moment of inertia about COM of combined system, and omega is the new angular velocity. So the moment of inertia of this system would be mr square plus mr square by 4 for the ring, because we are using the parallel axis theorem. Now we know that for the ring, the moment of inertia about its own center of mass is mr square, and about this point would be m into r by 2 ka whole square, as well as plus for this mass m, it would be mr square by 4 into omega. So the total moment of inertia will be 3 by 2 mr square omega, and if we balance the initial and final angular momentum, then mvr by 2 will be equal to 3 by 2 mr square omega. So cancelling this m with m, r with r, omega will be equal to v by 3r. So the correct answer would be option number B. Now let's move on the next question. In this question, there is a rod of length L and mass 4m. This rod is placed on a frictionless horizontal surface and it is free to move in any direction in any way. Another mass m, which is moving initially with the velocity of v, strikes this end B of the rod and comes to rest immediately. So now we have to find out the angular velocity of the rod just after the collision. So as we have already discussed in previous problems, that whenever there is some hinge, then we have to balance the angular momentum about hinge. But whenever the system is free to move, then we have to balance the angular momentum about the center of mass of the system, which is formed after the collision. Now you know that in this question it is given that this mass is not sticking to this point B. In fact, this mass would be at rest. So we have to balance the angular momentum about the center of mass of that system which is moving after the collision. So after the collision, only this rod is moving. So we have to balance the angular momentum about the center of mass of the moving system after the collision, which is the rod. So we're going to balance the angular momentum about point O. Now let us suppose that after collision, this rod is rotating with an angular velocity of omega like that. And therefore, if we balance out the angular momentum about O initially and about O finally, then the angular momentum initially, LO initially, would be equal to mv into L by 2, because this distance is L by 2. Now finally, the angular momentum about point O would be only due to the rod, and it would be I omega. So the moment of inertia of the rod about its own center of mass axis is ml square by 12. So this is 4m L square by 12 and omega. So this is ml square omega by 3. Now if we balance the initial angular momentum and the final angular momentum, then it is mvl by 2 and it is equal to ml square by 3 omega. So cancelling this m with m, L with L, omega will be equal to 3v by 2l. So this is the angular velocity with which this rod will move after the collision. Now let's move on the next question. In this question, it is given that there is a hollow sphere of mass m and some radius. It is rolling purely on a smooth horizontal plane. Its velocity is v naught and it collides elastically with another sphere, solid sphere of same mass and same radius. Now we have to find out the ratio of kinetic energy of B to the kinetic energy of A just after the collision. Now just after the collision, we know that when equal masses collides elastically, then their velocities gets interchanged, and therefore after collision I can say that the velocity of sphere B would be v naught and there would be no friction acting on this sphere B. Therefore it would be only translating with velocity v naught always. Now initially now after the collision, if we talk about this sphere A, which is a hollow sphere, so the sphere A would be was moving initially with velocity v naught, but just after the collision sphere A would be not translating and its velocity would be 0, because after the collision the velocity of B, which was initially 0, would be the velocity of A, which is now 0, because velocity gets interchanged. Now this sphere A would be rotating with angular speed omega, which is v naught by r, because there is no friction acting on A, which would decrease or increase its angular velocity. So the kinetic energy of A just after the collision would be half I omega square, and this is half I is the moment of inertia of this sphere about the center. So it is 2 by 3 m r square, and omega square is v naught square by r square. So cancelling this r square, this 2 with 2. So the kinetic energy of A is m v naught square by 3. Now the kinetic energy of B will be half m v naught square. Therefore, if we find out the ratio of kinetic energy of B to A, so Kb upon Ka is 3 by 2. So if we compare it with 3 to n, then n will be equal to 2. So the final answer is 2. Now we move on the next question. In this question, there is a uniform disk of mass 1 kg in radius 1 meter. It is moving towards right side on a smooth horizontal surface with velocity v naught is equal to 20, and angular velocity, which is in clockwise sense, it is equal to 4 radians per second. Now this disk is on the horizontal plane, and suddenly its top point is hinged by a nail so that it would not move. So this disk, which was initially free to move and rotate, is now hinged about this point. So as this disk is hinged, it would rotate now in anti-clockwise sense about this point, and we have to find out that new angular velocity. So in this question, we can balance the angular momentum about point A, because the torque about point A is 0, because point A is itself a hinge, and there is no force apart from the hinge force acting on this disk. So this and torque of this disk about the hinge point A would be 0, and therefore the initial momentum of the disk and the final momentum of the disk about this hinge, or we can say that about point A, will remain same. Now you can write down the initial momentum about A, angular momentum, as this disk is moving with velocity v naught, its center is moving with velocity v naught, and therefore the distance of point A from the center is r. So its angular momentum is anti-clockwise like that, and it is m v naught into r. So this is m v naught into r in anti-clockwise sense, but this disk is rotating about its center, so its rotational angular momentum is I omega, but in clockwise sense. This is very important to note, that I omega is in clockwise sense while mvr is in anti-clockwise sense. So the net angular momentum of this disk about point A is m v naught r, which is m is 1 kg and v naught is 20, and radius r of the disk is 1, and minus I omega, where I is the moment of inertia of the disk, which is mr square. So m is 1 and r square is also 1 divided by 2. So mr square by 2 is the moment of inertia of the disk about its center. And the value of omega is 4. So this negative sign indicates the fact that this translational angular momentum is in anti-clockwise sense, while this rotational angular momentum is in clockwise sense. So this is 20 minus 2 and this is equal to 18. So the initial angular momentum about point A is equal to 18. Now when A is hinged, then the final angular momentum about A would be in anti-clockwise sense, like that. And this is also due to the fact that you can see that the net angular momentum is in anti-clockwise sense, because the greater angular momentum is the anti-clockwise angular momentum. So the net initial angular momentum is in anti-clockwise sense. Hence, the final angular momentum would also be in anti-clockwise sense, and that would be equal to I moment of inertia about A into omega. Now the moment of inertia about A is mr square by 2 plus mr square into omega. So this is 3 by 2 mr square omega. Okay. So if we balance the initial angular momentum about A and the final angular momentum about A, then 18 is equal to 3 by 2, m is 1, r is 1, and omega we have to find out. So this is omega is equal to 12 radians per second. So this is the value of angular velocity just after hinging the point A. Now let's move on the next question. In this question, there are two balls A and B which are of same mass, same size and same shape. The ball A is kept at a height of h above the ground and ball B is kept at a height of h by 2 above the ground. Now this inclined plane is having some friction, so that these balls will always roll purely, and A is released and A will strike the ball B elastically, and it is also given that the ball B is kept stationary until A will strike ball B, which means that as soon as A will strike B, the ball B is released immediately. So we have to find out the kinetic energy of A just after collision with ball B. Now first of all, when this ball A will descend down and it will just on the verge of colliding with ball B, then work done by mg on A will be mg h by 2, because A has to descend down by a height of h by 2 to strike the ball B. So this work done by mg on ball A will be converted in kinetic energy of A, and therefore the kinetic energy of A just before the collision will be half mv square plus half I omega square, which is the rotational kinetic energy. Now this rotational kinetic energy is due to its rolling motion, and this is a solid sphere which has a moment of inertia of 2 by 5 mr square, and omega square is also equal to v square by r square by the condition of pure rolling. So you can see that the kinetic energy of A will be equal to 7 by 10 mv square initially, and this is just before the collision with ball B. Now after collision, elastic collision, we know that the velocities gets interchanged. So the velocity of A will become 0, but its angular velocity will still remain intact. So the kinetic energy of A after collision will be only half I omega square. So this half I will be equal to 2 by 5 m r square, and omega square is the angular velocity. Now we have to equate the initial kinetic energy just before the collision with work done by mg. So mgh by 2 will be equal to 7 by 10 mv square, and cancelling m with m, and this is 5. So v square is equal to 5gh by 7, and v will be equal to under root of 5gh by 7. Okay, so omega will be equal to v upon r. So this is v upon r, and omega is under root 1 upon r under root 5gh by 7. So if we substitute the value of omega in k dash, then it would be 1 by 5 m r square into omega square, which is 1 upon r square into 5gh by 7. So cancelling this r square with r square, 5 with 5, the kinetic energy of A will be mgh by 7. So the correct answer would be option number A. Now let's move on the next question. In this question, there is a uniform solid sphere which is placed on a smooth horizontal surface. An impulse I is given horizontally to the sphere at a height of 4r by 5 above the center line, and m and r are the mass and the radius of the sphere. Now we have to find out the angular velocity and the linear velocity of the center of mass of the sphere just after the impulse is given. So we know that impulse is always equal to change in momentum, and let us assume that its center starts to move with an velocity of v, and an angular velocity is omega about the center is imparted by this impulse to this sphere. So the impulse would be equal to change in momentum, and that would be final momentum minus initial momentum. So I would be equal to final momentum is mv and the initial momentum is 0. So I would be equal to mv. Okay. So this is the impulse, and if we have to find out v, then v is I upon m. Now to find out the omega, we can write down the angular impulse. Now the angular impulse is nothing but the product of linear impulse with the distance, where distance is the distance about the point from the point about which we are calculating the angular impulse. So if we are calculating the angular impulse j, let's suppose it is j, about this point O center, then it would be I into 4r by 5, because this distance is given as 4r by 5, where this impulse is imparted from the center line. So this is the angular impulse, and angular impulse is also equal to, j is also equal to the change in angular momentum. So j is equal to delta L. Now if we have to find out the change in angular momentum, so impulse is also calculated about center of mass, therefore change in angular momentum would also be calculated about center of mass. So j will be equal to L final minus L initial about O, and the final angular momentum about O. Now j is equal to I into 4r by 5, I into 4r by 5, I'll write it here. I into 4r by 5 is j, and that will be equal to final angular momentum about center of mass would be I omega, where I is 2 by 5 mr square and omega is angular velocity, and the translational angular momentum about O will be 0, because this O is itself moving with velocity v. So mvr would be 0 because r is 0. So you can see that omega will be equal to 2I by mr. So this is the angular velocity. Okay, now we have to find out the minimum time after which the highest point will touch the ground. So you can see that the highest point will touch the ground in the time when this solid sphere will rotate by an angle of pi by 2. In fact, pi, like that. So omega is equal to theta t, in fact theta upon t, and omega is t is equal to theta upon omega. So t is the time when b will touch the ground, will be pi upon omega, which is 2I by mr. And finally we have to find out the displacement of center of mass during this interval. So displacement of center of mass will be its velocity into time, and its velocity is I upon m, and time is pi mr upon 2I. So cancelling this I with I, m with m. So SO will be equal to pi r by 2. So now let's move on the next question. In this question, there is a rod which is kept on a frictionless horizontal surface. Its mass is 5 kg and its length is 90 meters. Now this rod is being struck by an impulse on one of its end, and the value of impulse is 3 Newton second, and this impulse is in horizontal direction, also perpendicular to the rod, and this impulse is removed after one time application. Now as a result of which this rod will start to rotate with some angular velocity, as well as it will acquire some linear velocity. So let us suppose that the linear velocity of the rod is v and its angular velocity is omega, like that, because impulse is struck at this point. So it would rotate this rod about the center in anti-clockwise sense. So we have to find out the force. First of all, we have to find out the omega and v. Then we'll talk the final question in the later part. So first of all, let us see that the impulse is equal to change in momentum. So impulse is 3 and change in momentum is final momentum minus initial momentum. Initially rod was at rest and the final momentum of the rod is m into v. So the mass of the rod is 5, so v is equal to 3 by 5. This is the velocity with which rod will move. Now the angular impulse is equal to the linear impulse into distance from the center, because we are calculating the angular impulse about center. So this is L by 2, and therefore this will be 3 into 45 centimeters. In meters it would be 0.45, because L is 90 and L by 2 would be 45, and in meters it would be 0.45. So this is the angular impulse. Now if we find out, we have to find out the omega. So angular impulse is also equal to the change in angular momentum about the same point O. So angular impulse is 3 into 45, which is 1.35, and that is equal to delta L, which is L final minus L initial. Now L initial is 0 and L final is equal to I omega. So 1.35, which is also 45 into 3. So let us write it as 0.45 into 3, and L final is m L square by 12. Now the m of the rod is 5 its L is 90, so this is 0.9 whole square by 12, ml square by 12, and omega is its angular velocity. So this omega would be equal to 0.45 into 36 divided by 5 into 0.81. So it is equal to 4. So omega is equal to 4, and this rod will be rotating with an angular velocity of 4 radians per second, like that. So we have to find out the force with which its half part will pull the second half part. So we know that if we assume the rod to be made up of two rods of length L by 2, L by 2, then the center of mass of this half part would be situated at this point, and this point, the center of mass, would be rotating like that, okay, in this circle. So the force which it would be experiencing would be centrifugal force M, which is M by 2, because we are talking about the half part. So M by 2, the radius of its circular motion is this one, L by 4. So mr omega square. So this is the force by which it would be pulled by the centrifugal force, and hence it would be pulling the lower half part with the same force. So F is equal to ml by 8, and omega is 4, so 4 square. So F will be m is I think 5, and 4 into 4 is 16, 16 by 8 is 2, and the length is given as 90 meters, so this is 0.9. So F will be equal to 9 newtons. So this is the force which the half part of the rod will apply on the other half part. Now we move on the next question. In this question, it is given that there is a uniform rod of mass m1 and length L, which is kept on a frictionless horizontal plane. A particle of mass m2 is moving with a speed of v0 perpendicular to the rod, and it strikes the rod at a distance of L by 3 from the center of the rod, where L is the length of the rod. Now we have to find out the velocity of the center of the rod as well as the angular velocity of the rod just after the collision, provided that it is mentioned in the question that this ball stops after striking the rod. So we know in these kind of questions we have to balance the linear momentum and the angular momentum, and linear momentum is balanced because there is no external force acting on the system in the direction of motion. So the net force acting on the system is 0. Therefore, the linear momentum of the system is conserved. Now the initial linear momentum was m2v naught, and the final linear momentum is m1 into v, where I have assumed that v is the velocity of the rod. So v will be equal to m2 v naught upon m1. Now we have to also find out the angular momentum of the rod. So in this kind of question, when the object is not hinged and it is free to move, then we always balance the angular momentum about the center of mass of the object, which is about the center of mass of the object which is moving after the collision. So after the collision, only rod is moving, and hence we have to balance the angular momentum about that center of mass of the rod. So the torque acting on the system is 0, obviously, about O, and therefore we can balance out the angular momentum of the system about O. So initial angular momentum about O was m2 v0 into L by 3, and the final angular momentum about O is, let's suppose this rod is moving with V and it is rotating with omega, so finally it is I omega, and the angular momentum mvr will be 0 because V is itself passing through the center. So L final about O will be I omega, where I is m L square by 12 and omega is omega. So if we balance the initial and the final angular momentum, then it is m2 v0 L by 3 will be equal to ml square by 12 into omega, and this m is the mass of the rod, which is equal to m1. So this is m1, and cancelling L with L, 3, and this is 4. So omega will be equal to m2 v0 by m1 L, and this is 4. So this is the value of omega. So we have to find out the velocity as well as omega, and these are the final answers. Now we move on the next question. In this question, there is a ball of mass m, and this ball is moving with a velocity of u. This ball strikes this rod at some distance x from the hinge, and the mass of the rod is m and its length is L. So we have to find out the value of x for which there would be no hinge force that will act on the rod just at the time of collision. So to solve this question, let us assuming that rod was not hinged. So if this rod was not hinged, then if this ball strikes the rod and comes to rest, then let us suppose that rod starts to rotate with an angular velocity of omega, and its center starts to translate with the linear velocity v. So if we talk about this point which is hinged in the real case, so the velocity of this point would be v due to the translational motion and L by 2 omega due to the rotational motion. So if you can easily predict that if v is greater than L by 2 omega, then I'm writing it down that if v is greater than L by 2 omega, then the velocity of point A will be in forward direction, v minus L by 2 omega in forward direction in the right hand side, and therefore hinge force will be acting in the left hand side to stop this point A, because after hinging this point A, this point will not move. So hinge force will restrict the point A, and it would not allow the point A to move. So hinge force in this case would be in backward direction. If v is less than L by 2 omega, then the net velocity of A would be in backward direction, and it is L by 2 omega minus v. And in this case, hinge force will be acting in the forward direction, because it would again not allow the point A to move in the backward direction. But the question which we are concerned is the fact that the hinge force will not act. So if I'm writing it with this different color, so if v is equal to L by 2 omega, then obviously point A will not move, and therefore there is no tendency of point A to move, and hinge force in that case will be 0, because hinge force will only act when A will show the tendency to move. So if A has 0 velocity, then hinge force in that case would be 0. So this is the related concept. So we are we now have L by 2 omega. V is now equal to L by 2 omega, so that hinge force is 0. Now the second, we can if the hinge force is 0, then we can balance the initial and the final momentum. So mu will be equal to mv, where v is the velocity of the center of the rod. So v is equal to u, and we can also balance the angular momentum about the hinge or about any point. So let us balance about hinge only. We can balance about any point, but we are balancing about hinge. So mu into x is equal to I omega, where I is ml square by 3, the moment of inertia of the rod about the hinge, and omega is the angular velocity. So omega will be equal to 3ux by L square. Now we know that V should be equal to L by 2 omega. So if hinge force is 0, V should be equal to L by 2 omega, and V is equal to U, you can see that, and this is L by 2, and omega is equal to 3ux by L square. 3ux by L square. So cancelling this L with L and U with U, x is equal to 2 by 3L. So the value of x for which this rod will not experience any hinge force is 2 by 3L. So this is the final answer. Thank you.